Okay, electronegativity is defined as the atom's affinity to attract electrons or to desire electrons. Indicate the trend in electronegativity of the elements with the group and period. The trend is that whenever you see the word trend, it's looking for, oh my good gracious. Whenever you see the word trend, once again, one more time. It really doesn't like me, does it?
Oh my.
Woo.
Sounds like
Wow. Whenever you see the word trend, it's looking for as you blank, it blanks. Okay? So in the periods, so how about as we go left, right in the period, what happens? The electronegativities? The electronegativities do what? Increase. Because you're getting to be more non-metals. So therefore they are going to want electrons. Right? Okay. Describe the difference between a polar and a non-polar bond. A non-polar bond has an equally shared pair of electrons. Okay? I want to see the word shared pair of electrons for both, where non-polar would be equally shared and polar would be unequally shared pair of electrons. But it's important that we understand that they're both shared pairs of electrons. Therefore, we're talking about covalent bonds, because that's the definition for a covalent bond. Okay? Happy? Okay, and then we went through some of these. We went through A to G already, but let's try a few more. B to F, the arrow goes towards the F NCl. Are you sure? You looked it up on the periodic table? Yeah? ZBr. Tricky question here. Pardon me, Logan? It's ionic. Metal, non-metal. Whoa. So not just for these ones I'd have a partially negative, partially positive. This is negative. This is positive. I'd want to double check to make sure the electronegativity difference is indeed greater than 1.7 or less than 1.7 to see whether it is indeed ionic or covalent. But anyway, okay. Et cetera, et cetera, et cetera. Okay. Question 5 then. Everybody ready for question 5? Whee. Okay, that's number 4. We'll start at 4 because we did 1, 2, and 3 together already. So PCl3 looks like this in its structural. The bonds are polar or non-polar? Polar. If I had to draw arrows, they would go towards the Cl's, correct? Oh, pardon me, this is about shape, isn't it? What shape does it have? And what shape is the overall molecule then? Polar. Hang on though. If I drew that differently, it would look symmetrical. If I drew it like this, it would look symmetrical. So why isn't this non-polar molecule? Yes?
Because phosphorus has a lone pair on top.
Right. And that lone pair pushes the chlorines downward, giving it that pyramid shape, or like I say, a tripod, right? Tripod. And because it's tripod, it's going to be unequally balanced, not symmetrical. And therefore it'll tip if one end ate all the pies. And so this end will be relatively negative down there at the bottom of the tripod. Get it? What grade are you in?
10.
Yeah. This is hard for grade 10. Did I say that yesterday? Okay. What I didn't say yesterday though is you just have to understand that this is, in fact I'm just going to pause this for a second. Okay. And on that note. Okay, BF3. Now this, no lone pairs, right? Do you see why they put these right beside each other? 4 and 5? Do you see the comparison I'm trying to have you do with 4 and 5? 4 looks like a tripod with a camera on top, the camera being the lone pairs. This, however, isn't pyramidal, but rather it's trigonoplanar. It's flat. So it looks like this. B, F, 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 like a peace sign, completely flat. So now I have a flat seesaw, right? And so each of these bonds are polar, right, everybody? Is that what you got to? But the overall molecule is nonpolar. Because imagine this piece-shaped looking seesaw, and I've got fat elephant, fat elephant, fat elephant, and that mouse is sitting right in the middle. Oh dear. That mouse is sitting right in the middle of that seesaw. The mouse isn't going to move anywhere. The fat elephants don't move anywhere. Everything's perfectly balanced because he's in the middle of the web. And the web is flat. Everybody get? Can everybody visualize? Can everybody see the differences between 4 and 5 and why the end result is one of polar and one of nonpolar? Say yes or say no.
Yes.
Nick.
What's boron's don't diagram structure?
So therefore, F, right? Okay, and those are going to get as far away from each other as possible, which is why they are exactly, what's 360 divided by 3, 120 degrees apart from each other. Okay. Okay, the next one is V-shaped. Oh, hello. So S, Cl, Cl, V-shaped. Polar, non-polar bonds? Polar, non-polar molecule? Are you getting the hint that every O and S and group 6 is V-shaped? And they are then therefore going to be polar? So H2O was polar. H2S would be V-shaped and polar. Let's go Cl2S would be V-shaped and polar. Cl2O would be V-shaped and polar. You seeing this yet? So it's not like a new experience every time. You're starting to get the feeling, group 6, V-shaped, polar. Not because you're memorizing it, but because you want, because you're seeing the pattern. Right, NH3, we pointed out this pattern before. We knew that this would be pyramidal. And the bonds are polar, and the overall molecule is polar. OCl2. V-shaped, polar, polar. Next one. This is another classic, right? Which we're hopefully by now logged into our memories. Trigonoplanar. Very good. Bonds are polar, but the overall molecule is nonpolar because it is symmetrical. Symmetrical. Is 10 the last one?
No.
Okay, so number 10, AS, what group is it in? 5. So you've never seen it before, but you have seen nitrogen before. It's in group 5. It's one of our classic examples. Cl has one stick just like H has one stick. So actually 7 and 10 really aren't any different from each other. Do you see that? At first glance, it looks like a brand new thing you've never seen before. At second glance, though, you should be like, oh, easy. ASCL, pyramidal, just like number 7 was, polar just like 7 was, and polar just like 7 was. Is that right? I would want to double check the electronegativity differences of AS and CL, but okay, just because you don't deal with AS very often, so you would just want to double check that. Okay, move the thing up. Please, pretty please. The sugar on top. Oh, that's the end.
It says drag.
That's the end anyway. Right. CO2, I said to you a couple days ago that that is a good one to have memorized. You can figure it out. You could go and do the dot and cross diagram. It just takes you longer. But it comes up so often that it's pretty good to know it's that without having to do the dots and crosses. You have the capability of doing it by dots and crosses, but it's so much faster if you just have it as one of the ones in your back pocket. Shape. Linear. Why not V-shaped?
A double bond.
Because of the double bonds? Because of the absence of what made the V-shaped one V-shaped, not linear? The lone pairs. There are no lone pairs to push those double bonds down. There's nothing else to interfere. This and this are the only things that have electrons in them. So they're going to be as far away from each other as possible. Therefore, they're going to be 180 degrees from each other. Are the bonds polar or non-polar? Polar. In this case, they go out. And like a perfectly matched game of tug or war, it's not going to move. Non-polar. Okay? C2H2, you might have had to do a dot and cross diagram for. I don't know, but you end up with this. Did you get that? Well done. Shape? Linear. Even though you don't have it as an example, you kind of go, oh, no lone pairs to push it apart, far away as possible, linear. Bonds are? Molecule is? Good. Now this.
Isn't there two different bonds though? There's a bond between the two C's and a bond between the H and the C.
Yes, so this bond would be, oh, I see what you're going. And then the C triple bond, C would be non-polar. Is that what you're saying? That's true. That's true. Good. Any other questions or comments? If I can't even see you, chances are you can't see me. Yep. Okay.